Hi there, I'm Sridhar and I'm excited to share my knowledge and experience in transmission line construction with you. In this series, my goal is to equip engineers and managers with the essential know-how they need before stepping into the field and taking charge of their projects. We'll dive into everything from the basics of construction and execution planning to tendering, budgeting, and even touch on the engineering ethics that are so important in our profession. Each week, I'll be posting a new video. In each chapter, we'll explore relevant technical topics, discuss ethical considerations, and wrap up with a thought-provoking quote. So, stay tuned. There's a lot to cover. Disclaimer. Just a quick note. The content in these videos is meant for informational and basic educational purposes only. These videos aren't intended to provide professional advice or endorsements. This helps set the right expectations about the nature of what we're sharing, especially since we draw on material from various sources under the principle of fair use. Welcome to Chapter 1 of our study on transmission line construction. In this first chapter, we're diving into the basics. Let's get started with the fundamentals. Today, we're kicking off with Chapter 1, where we'll cover the fundamental knowledge that's crucial for understanding the technical aspects and importance of the topics we'll dive into in future chapters. In transmission line construction, we'll explore some core subjects. First up, we'll start with an introduction to power transmission lines. What exactly are power transmission lines? Why do we need them? And what are the key components and their uses? Next, we'll move on to the basics of electricity. We'll discuss electricity as a fundamental form of energy which comes from the movement of charged particles, usually electrons, through conductive materials. We'll also look at its critical role in modern society, powering everything from lighting and heating to electronic devices and industrial machinery. Plus, we'll explore the formation of electricity and essential properties like charge, current, voltage, and resistance. Then, we'll cover electricity generation. How is electricity generated? What are the different methods of generation? And what are the requirements and purposes of these methods? After that, we'll discuss prerequisite activities. We'll take a look at the key activities that are closely linked to the main tasks in transmission line construction. Following that, we'll dive into construction activities. We'll go through the construction process in detail, from the initial survey all the way to handing over the project. And finally, we'll wrap up with estimation, bidding, and site budget. We'll get into the processes involved in estimation, bidding, and managing the site budget as the project nears completion. Let's get started. Introduction to power transmission lines. High-voltage transmission lines, often called power lines or electrical transmission lines, are essential components of the electrical grid. They transport electricity from power generation sources, such as power plants, to substations closer to end users, including homes, businesses, and industries. These transmission lines are specifically designed to transmit electrical energy over long distances with minimal energy loss, ensuring efficient and reliable delivery of electricity where it's needed. Purpose of transmission line construction. Before delving into the details of transmission line construction, it's important to understand the core objectives behind this infrastructure. Purpose. The main goal of constructing high-voltage transmission lines is to transmit electricity from distant power generation facilities to areas with electricity demands. Often, power plants are located far from population centers, making these lines essential for bridging the gap. Planning. Successful transmission line projects require thorough planning. This process involves understanding the demand for electricity, the available generation sources, and the best route for the transmission line to minimize impact and cost. The power transmission process. The electrical grid relies on three primary processes to deliver electricity: generation, transmission, and distribution. Power generation. This is the process of converting various energy sources, such as fossil fuels, nuclear, solar, wind, hydro, and geothermal, into electricity. The choice of generation method depends on resource availability, cost, environmental impact, and regional policies. Given the growing concerns about climate change, there is an increasing emphasis on sustainable and renewable power sources, which contribute to a cleaner energy landscape. Power transmission. Once electricity is generated, it is transported through high-voltage transmission lines to substations closer to consumption areas. High voltage is essential for efficient long-distance transmission, as it minimizes energy loss due to resistance in the wires. These lines form the backbone of the electrical grid, connecting power generation sources to distribution networks. Power distribution. At substations, the high-voltage electricity is transformed to a lower voltage suitable for safe distribution. From there, the electricity travels through lower voltage distribution networks, eventually reaching homes, businesses, and industries. In our previous topic, we briefly covered the basic requirements for transmission line construction to provide a general understanding. In later chapters, we will dive into detailed construction activities. For now, let's shift our focus to our first fundamental topic: understanding electricity. In this section, we will explore the concept of electricity, starting from its definition and progressing to the atomic structure that explains how electrical energy is generated and utilized. What is electricity? Electricity is a fundamental form of energy that results from the movement or flow of charged particles, primarily electrons, through conductive materials. This movement of electrons allows electrical energy to be harnessed for various applications, from powering appliances to lighting homes. To fully understand electricity, it's important to grasp the structure of atoms, which are the fundamental units of matter. Now let us understand atom components of an atom. Atoms are the smallest units of a chemical element that retain the properties of that element. Each atom consists of a nucleus and surrounding electron shells. Protons. Protons are positively charged particles located in the nucleus of an atom. Each proton carries a fundamental unit of positive electric charge, which is equal in magnitude but opposite to the charge of an electron. The number of protons in an atom determines its atomic number and defines the specific element, e.g., hydrogen has 1 proton, carbon has 6. Neutrons. Neutrons are neutral particles found in the nucleus and carry no electric charge. They contribute to the mass of the nucleus and play a crucial role in stabilizing the atom. Isotopes of an element differ in the number of neutrons they contain while retaining the same number of protons, affecting their stability. Electrons. Electrons are negatively charged particles that orbit the nucleus in defined regions known as electron shells or energy levels. Each electron carries a fundamental unit of negative electric charge and is attracted to the positively charged nucleus by electromagnetic force. In a neutral atom, the number of electrons typically equals the number of protons, resulting in no net electric charge for the atom. The movement of electrons either through a conductor or between atoms establishes electrical currents. When electrons move from one atom to another, they create an electric current, which forms the basis of how electricity operates in circuits and power systems. Let us further explore the function of the atom. In atomic structure, the interaction between protons, neutrons, and electrons defines the behavior and properties of matter. Here's a detailed look at these interactions. Components of the atom. Atoms consist of two main parts, the nucleus and electrons, each playing a crucial role in the atom's function. Nucleus. The nucleus is the dense center of the atom, containing two types of particles. Protons, positively charged particles located in the nucleus. Each proton carries a fundamental unit of positive electric charge. The number of protons determines the atomic number, which defines the element. Neutrons, neutral particles located in the nucleus that carry no electric charge. Neutrons contribute to the atom's mass and play a critical role in maintaining the stability of the nucleus. In electrons are negatively charged particles that orbit the nucleus in various energy levels, also known as electron shells. Each electron carries a fundamental unit of negative electric charge. Electrons are much lighter than protons and neutrons and are responsible for the atom's chemical behavior. The nucleus, which contains positively charged protons and neutral neutrons, forms the core of the atom. Electrons, which are negatively charged, orbit the nucleus in shells. The interaction between these charged particles determines the atom's stability, electrical properties, and overall behavior. Next, let us understand the atomic stability and ionization. Stable atom. An atom is considered stable when the number of protons equals the number of electrons. This balance results in no net charge, allowing the atom to remain neutral and maintain its integrity. Positively charged atom. When the number of protons exceeds the number of electrons, the atom carries a net positive charge. This occurs when an atom loses one or more electrons and is referred to as a cation. Negatively charged atom. Conversely, if there are more electrons than protons, the atom carries a net negative charge. This happens when an atom gains extra electrons, resulting in an anion. Ionized atoms. Both positively and negatively charged atoms are collectively known as ionized atoms. Ionization occurs when an atom either loses or gains electrons, leading to a change in its electron configuration. The balance of protons and electrons determines the charge and stability of the atom. Further understand what is electron shells and valence electrons. Electrons are negatively charged particles that orbit around the positively charged nucleus, containing protons and neutrons, at varying energy levels. These energy levels form what we refer to as electron shells. The number of electrons each shell can hold is determined by quantum mechanics. The innermost shell, closest to the nucleus, can hold a maximum of 2 electrons. The second shell can hold up to 8 electrons. The third shell can generally accommodate 18 electrons, although it often holds only 8 in many elements before starting to fill the next shell. These shells are arranged sequentially, with each shell representing a higher energy level than the one closer to the nucleus. Now, understand what is attractive forces and valence electrons. When electrons are attracted to the nucleus by the positive charge of the protons, it's called the attractive forces. The closer an electron is to the nucleus, the stronger the attractive force it experiences. As a result, electrons in the innermost shells are more tightly bound to the atom. However, electrons in the outermost shell, also known as valence electrons, are further from the nucleus, meaning they experience less attraction and are held more loosely. This weaker attraction allows the valence electrons to be more easily influenced by external forces, making them more likely to participate in chemical reactions and electric current flow. Valence electrons and electricity. When the valence electrons being loosely held shall have a higher likelihood of jumping from one atom to another, especially when influenced by an external force, such as an electric field. This ability of valence electrons to move or jumping between atoms is the fundamental in the formation of electrical conductivity or electricity. When an electric field is applied to a material, especially conductors like metals, the valence electrons move freely, creating an electric current. In brief, let us summarize what are metals, nonmetals, electron shell, and valence electrons. Metals. In metals, valence electrons are free to move from one atom to another, which is why metals are excellent conductors of electricity. Nonmetals. Nonmetals, on the other hand, tend to hold their valence electrons more tightly, making them poor conductors of electricity. Electron shells represent the energy levels at which electrons orbit the nucleus, with the innermost shells being more tightly bound, and the outermost shells, valence electrons, being more loosely bound. Valence electrons are the outermost electrons and play a key role in electricity because their movement from one atom to another enables the flow of electric current. This property is fundamental to how electrical circuits and conductors function. Let's take a moment to understand conductors and insulators, as this concept plays an important role in our study. Conductors, insulators. Conductors are materials whose atoms have loosely held valence electrons, making it easy for these electrons to move between atoms. Most metals, such as copper and aluminum, are excellent conductors due to their atomic structure. When an electric potential, voltage, is applied, the valence electrons in conductors can move freely, allowing electricity to flow easily. Insulators are materials that hold their electrons tightly and do not share them with neighboring atoms. Examples include plastic, rubber, and glass. And insulators prevent the flow of electrons, which makes them crucial for protecting against unwanted electric currents and ensuring safety in electrical systems. Nonmetals. Nonmetals, on the other hand, tend to hold their valence electrons more tightly, making them poor conductors of electricity. Electron shells represent the energy levels at which electrons orbit the nucleus, with the innermost shells being more tightly bound and the outermost shells, valence electrons, being more loosely bound. Valence electrons are the outermost electrons and play a key role in electricity because their movement from one atom to another enables the flow of electric current. This property is fundamental to how electrical circuits and conductors function. Static electricity. When two objects are rubbed together, electrons are transferred from one material to another. For instance, rubbing your feet on a carpet moves electrons to the carpet, leading to a positively charged body. Upon touching a conductive surface, such as a doorknob, the excess electrons can transfer back to your body, causing a small electric shock. In continuation, let us know flow of electricity and resistance. In a battery, the positive and negative terminals create an electric potential. When a conductor, such as a copper wire, is connected, the battery pushes electrons through the wire, creating a flow of electricity. This establishes a circuit. When resistive elements, like a light bulb, are added to the circuit, they restrict the flow of electrons, causing the electrons to lose energy in the form of heat and light. For example, the tungsten filament in a bulb provides resistance, which lets it glow as the electricity flows through it. Understanding electric current. In this section, we will explore the concept of electric current, how it flows through a conductor, and its significance in powering electrical devices and systems. What is electric current? Electric current is defined as the flow of electric charge through a conductor, typically measured at a specific point in a circuit. This flow is primarily due to the movement of electrons, which travel from one atom to another within the conductive material. Direction of current. In a circuit, electrons move from the negative terminal to the positive terminal of a power source. However, by convention, electric current is considered to flow in the opposite direction, from positive to negative. This convention dates back to Benjamin Franklin's time before the discovery of the electron. Measurement of current. The unit of measurement for electric current is amperes. 1 ampere is defined as the flow of 1 coulomb of charge per second. Coulombs and electrons. A coulomb is a large quantity of electric charge, approximately equivalent to 6.28 billion 6.28 x 1018 electrons. Therefore, when a current of 1 ampere flows through a circuit, it means that 6.28 x 1018 electrons pass through a given point in the circuit every second. Current measurement. Current can be measured using an ammeter, which is connected in series with the circuit to provide a reading of the flow of electrons at that point. Otherwise, you can consider in a circuit the number of electrons passed through at particular point per second can be calculated. Understanding voltage. Voltage is a fundamental concept in the study of electricity, playing a crucial role in electrical circuits and the flow of current. Here, we will explore what voltage is, how it relates to other electrical parameters, and its significance in a circuit. What is voltage? Definition: voltage, also known as electric potential difference, is the measure of the electric potential energy per unit charge between 2 points in a circuit. It represents the driving force that pushes electrons through a conductor. Potential difference. Considering a battery, one terminal has an excess of negatively charged particles, electrons, while the other terminal has positively charged particles, protons. This difference in charge creates a potential difference between the two terminals. The larger the difference, the greater the potential for electron flow, thereby increasing the voltage measurement. Voltage is measured in volts, V, not ohms. Ohms measure resistance, whereas volts measure the electric potential difference. Specifically, 1 volt is defined as the potential difference that will drive 1 ampere of current against 1 ohm of resistance. Understanding voltage in circuits. Voltage can be viewed as the force that pushes electric charge, electrons, through a circuit. You can think of it as the pressure in a water system. The higher the pressure, voltage, the more water, electric charge, flows through the pipes, conductors. Otherwise, you can consider voltage is the uniform quantum of electrons flow in a conductor. In our earlier topics, we learned that electricity is generated when electrons move from one atom to another. Now let's delve into how electricity is produced on a larger scale and explore the differences between alternating current, AC, and direct current, DC. Let us understand briefly how electricity is produced. As we are covering this subject separately in our study chapter, electricity is typically generated in power plants using various energy sources such as fossil fuels, nuclear energy, hydroelectric power, wind, and solar energy. The most common method involves using mechanical energy to rotate a turbine, which in turn drives a generator. The generator contains coils of wire and magnets. When the turbine spins, it causes the magnets to rotate around the coils of wire, creating a flow of electrons and thereby generating electricity. Even though we've touched on the basics of electricity generation, it's crucial to dig deeper into the fundamental principles that govern how electricity is produced. Understanding these basics not only gives us a clearer picture of the entire process, but also enables us to appreciate the complexities involved in generating and delivering power to our homes and industries. Electricity generation starts with converting energy from various sources into electrical energy. The key principle here is electromagnetic induction, discovered by Michael Faraday back in the 19th century. According to Faraday's law of induction, when the magnetic field within a closed loop of wire changes, it creates an electromotive force, or EMF, which is basically voltage in the wire. This process forms the backbone of most power generation methods today. Now let's break down some important concepts. First, the electric field. It's created by stationary charges, and its strength depends on the amount of charge present. Think of it as the force a charge would feel in the company of other electric charges. Next, the magnetic field. This is generated by moving charges, like a current flowing through a wire. The faster the charges move, or the stronger the current, the stronger the magnetic field. Together, these fields play a crucial role in how we generate and use electricity. Let's take a closer look at how an electromagnetic field works. When a charged particle, like an electron, moves, it creates both an electric field and a magnetic field. These fields are perpendicular to each other and to the direction in which the particle is moving. Here's the interesting part. A changing electric field generates a magnetic field, and a changing magnetic field generates an electric field. This continuous interaction is what allows electromagnetic waves to propagate. Now let's dive deeper into how a magnetic field can generate current. As the image shows, when current flows through a conductor, it produces a magnetic field. The stronger the current, the stronger the magnetic field. But this process also works in reverse. If you introduce a magnetic field around a conductor, you can produce current. This principle is fundamental to how we generate and harness electricity in many of our technologies today. Faraday's law of induction explains how we can generate an electric current in a conductor by changing the magnetic field around it. When the magnetic field around a conductor changes, it induces a voltage in that conductor. This is the fundamental principle behind how electricity is generated in power plants. Let me emphasize this once more. Whenever the magnetic field around a conductor changes, it induces a voltage in the conductor. This core principle is essential to understanding how we generate electricity on a large scale. Let's explore how current is generated through magnetic induction. In picture 1, you can see that when a magnet moves through a coil of wire in a forward direction, it generates a current in the conductor. Since the magnet and the current both move in one direction, this type of current is called direct current, or DC. You can observe this on the ammeter needle. Now refer to picture 2. Here, when the magnet stops moving, the current also stops flowing. Again, you can see this on the ammeter needle. Finally, picture 3 shows what happens when the magnet moves in the reverse direction. The current is generated again, but this time it flows in the opposite direction. When you move the magnet back and forth, the current produced alternates directions, creating what we call alternating current, or AC. When a stronger magnet is used, it generates a higher voltage, and using a larger coil can produce a stronger current. However, there are limitations when relying on magnetic induction with a permanent magnet, especially if we're trying to generate higher voltage. This is due to the magnet's size and strength, which can diminish over time. To overcome these limitations, we can use an electromagnet, as we learned in a previous study. By adjusting the magnetic field strength of an electromagnet through the induced voltage, we gain better control over both the current and the voltage. This flexibility makes electromagnets more effective for generating electricity, especially when higher voltages and currents are needed. Instead of moving the magnet inside the coil, we can generate current more efficiently by rotating the magnet near a stationary coil. The strongest magnetic fields are found at the ends of the magnet, its north and south poles. As the magnet rotates around the coil, the magnetic field strength increases when one of these poles approaches the coil. This stronger magnetic field pushes more electrons to flow in one direction, generating a current. This method is commonly used in generators because it's a more efficient way to produce electricity. As the magnet moves away from the coil, the magnetic field weakens, reducing the flow of electrons until it eventually stops. But when the opposite end of the magnet approaches, the electrons start flowing in the opposite direction, creating an alternating current, or AC. When the magnet rotates continuously, it generates an AC current that forms a complete sine wave, reflecting the back-and-forth flow of electrons. Let's dive into three-phase current generation. When a magnet rotates near a single coil, current is only generated at specific angles where the coil aligns with the magnetic field. This means other areas of the magnetic rotation go unused, leading to inefficiencies. To make better use of the magnetic field, we can add a second coil positioned 120 degrees from the first and a third coil 120 degrees from the second. By evenly spacing these three coils around the rotating magnet, we ensure that current is generated more consistently and efficiently throughout the entire rotation. As the magnet's ends pass by each coil at regular intervals, electrons flow first in one direction and then in the opposite direction. This creates a three-phase AC current with the correct frequency. This is the fundamental process of electricity generation. In our next chapter, we'll dive into large-scale electricity generation and explore the different methods used to power our world. We've now wrapped up Chapter 1 of our journey into transmission lines. Along the way, we've explored some essential concepts, including the basics of atoms, nuclei, and electrons, how electrons are generated, the difference between conductors and insulators, the nature of electric and magnetic fields, how electromagnetic fields work, the fundamentals of electricity generation, understanding current and voltage, the distinctions between alternating and direct current, and finally, the production of single-phase and three-phase current. Great job making it through this first chapter. As we move through our study program, we'll be adding valuable lessons at the end of each chapter. Today, let's dive into the topic of professional ethics, what they are, and why they're so crucial for us as professionals. Professional ethics encompass the moral principles and standards that guide our behavior within our chosen professions. Typically outlined in a profession-specific code of ethics, these guidelines ensure that we uphold integrity, responsibility, and respect in our interactions with clients, colleagues, and the broader community. Let's break down some key components. Integrity. Professionals should always act honestly and be truthful in their dealings. Avoiding deceptive practices and upholding fairness are essential. Confidentiality. As professionals, we often handle sensitive information. It's crucial to maintain confidentiality, ensuring that private data stays protected. Competence. Staying skilled and knowledgeable in our field is a must. This often means continuous learning and keeping up with the latest advancements. Responsibility. We have a duty to act in the best interests of our clients or the public, making sure our work does no harm and contributes positively to society. Respect. Ethical behavior also means treating everyone with dignity and respect, regardless of their background, status, or beliefs. Accountability. Finally, we must take responsibility for our actions and decisions, being ready to explain and justify them when needed. Now, why are professional ethics so important? Building trust. Ethical behavior helps build trust between professionals and their clients or the public. Trust is key to effective relationships and long-term success. Enhancing reputation. Sticking to professional ethics boosts both our personal reputation and that of our profession as a whole, leading to greater credibility and respect. Legal compliance. Many ethical standards are also legal requirements. By adhering to them, we can avoid legal issues and keep our licenses or certifications in good standing. Social responsibility. Lastly, professional ethics ensure that we contribute positively to society and avoid practices that could harm individuals or communities. In summary, professional ethics guide us to conduct ourselves in a way that is honest, responsible, and respectful, ultimately benefiting society and maintaining the integrity of our profession. Among the key components of professional ethics, today we will focus on one of the most essential traits for engineering proficiency: integrity. Integrity is a fundamental ethical principle that involves being honest, upright, and morally sound in one's actions, decisions, and interactions. It requires adherence to moral and ethical principles, even when faced with challenging choices or temptations. Integrity means aligning one's words with one's deeds, making it a highly valued trait in personal, professional, and societal contexts. It serves as the foundation of trust, credibility, and ethical conduct. In professional settings, integrity is reflected in several qualities: honesty and truthfulness, being open and sincere in all communications and actions; consistency and reliability, following through on commitments and maintaining stable, dependable conduct; ethical behavior, acting in alignment with ethical standards and codes of conduct; trustworthiness and credibility, building confidence in others through honesty and integrity; accountability and responsibility, taking ownership of actions and accepting the consequences of decisions; respect for others, treating everyone with dignity and respect regardless of background or status; professionalism and ethical conduct, upholding high standards in all professional dealings and relationships. By embodying these principles, individuals with integrity contribute to a positive work environment and foster trust and respect within their professional community. In summary, professional ethics guide us to conduct ourselves in a way that is honest, responsible, and respectful, ultimately benefiting society and maintaining the integrity of our profession. Today's quote is from Dwight D. Eisenhower. "The supreme quality for leadership is unquestionably integrity. Without it, no real success is possible, no matter whether it is on a section gang, a football field, in an army, or in an office." This quote highlights that integrity is the cornerstone of true leadership. Without it, any success you achieve isn't authentic or lasting. Whether you're leading a small team or managing a large organization, integrity is what makes real success possible. Organization. A leader's integrity is what earns them trust, respect, and ultimately, real success. As we wrap up our session, I encourage you to subscribe and hit the bell icon so you won't miss any of our upcoming chapters. It's your gateway to mastering transmission line supervision. That brings us to the end of today's chapter. Next time, we'll be diving into the fascinating topic of power generation. Until then, take care, and thanks for watching. Hi there, I'm Sridhar Chandrasekharan, and I'm excited to share my knowledge and experience